Okay, so the HL aspect of electrochemistry focuses on a couple of things. One, cell potential. Two, aqueous electrolytic cells. And then electroplating. Those are the three main ideas. And so we will go through here, we'll do cell potential. And offshoot that, we will use the delta G equals negative NFE equation. And then we'll talk about aqueous electrolytic cells. And then we will talk about electroplating. Those are the three major concepts in HL. The majority of this lesson will be probably cell potential, to be honest with you. Okay, so what is cell potential? Okay, so essentially standard cell potential, which is E naught, is the cell potential relative to the standard hydrogen electrode, or the SHE for short. Okay, so what scientists did was they hooked up half cells to a standard hydrogen electrode cell and gave the potential of the standard hydrogen electrode cell as 0. And whatever the reading read, they assigned that to the other cell. And so for a diagram here that we've seen kind of before, it looks like this. Okay, they hooked it up so that this was the anode and this was the cathode. Okay, and so if the voltage read positive, then that means this was oxidizing, this was reducing, so this is a better reducer. If it read negative, that meant the left one was oxidizing and the hydrogen was reducing. Okay, because the sign, the value of the voltmeter tells you which direction the electrons are flowing. Okay, and you're setting it up as if the hydrogen is the anode. So if you get a negative number, then you set it up backwards. That's what it's trying to tell you. Okay, so a couple of these values are a little different for IB. This is 100 kPa, 1 molar. That's the main one. 298 Kelvin, things like that. I don't think they're going to have you recite all the characteristics of a standard hydrogen electrode. They're trying to minimize memorization and recall, so you probably won't see that as a big emphasis. The idea, though, is that when you compare different cell potentials, and I'm going to write these down from the data packet. So, for example, zinc is negative 0.76, and tin, 2 plus, reduction potential is negative 0.14. Okay, the cell potential helps you determine which one's the better reducer. In this context, because these are all reduction potentials. Okay, so comparing these two right here, if they're both reduction potentials, the more positive one is better reducer. Okay, so which one's going to be the better reducer? SN. Okay, so SN2 plus is better reducer. And notice that I'm specifically saying SN2 plus. You won't say SN is a better reducer because SN2 plus is what's actually reducing. That's a very common multiple choice question. They'll say, given the two cell potentials, which species is the best reducer? And they'll have SN, SN2 plus, ZN, and ZN2 plus. So it's SN2 plus is the best reducer. Okay, so therefore, what's the better oxidizer? Oops. No 2 plus. Just zinc. Because it's the reverse reaction that's occurring. So if you're going to compare two numbers, make sure they're the same type of reaction. They could both be oxidation, then the more positive one would be the better oxidizer. So your rule of thumb is, whichever way the reactions are written, if they're the same, the more positive one is the better at doing that type of reaction. That's the concept. Okay? So if I give you oxidation reactions, the most positive one's the best oxidizer. I give you all reduction reactions, the most positive one's the best reducer. So keep that in mind. Okay? Don't just always assume the most positive one's the reducer, because then the IB will switch it around to see if you really understand what's going on. Like, if I'm the IB, what I do is this. I take a couple of these, like on the multiple choice, and I write this, and then I write, let's say, I'm trying to find out, make sure I write the right one. So Ag yields Ag plus electron. This, and then I write, I don't know, let's see. Like this. Let's say I give you 4 different cell potentials. Notice they're not all the same type of reaction, right? 2 of them are reduction, 2 of them are oxidizing. Okay? If I'm the IB, I ask you, which of these is the best reduced? What's the best reducing species of these half reactions? Okay? So my question here is, what is the best reducing species? Okay? Yes, Nabil.
Wait, are we like answering this?
Yeah, if you want to answer it.
Is that Ag plus?
Okay, why is it Ag plus?
Because it would be the most positive cell potential if it was the reduction.
You have to flip it. So what Nabil did was he flipped this, because this is oxidation, so this should really be plus 0.80, and this should be plus 0.34. So this means Ag plus is the best reducing species. Exactly. But again, if a student just memorizes the most positive one, and they don't pay attention to the reactions, they're going to say SN2 plus, because that's the most positive one here that they see here. So that's how the IB tests to make sure you didn't memorize something and that you actually understand what's going on. Does that make sense? Yeah.
And you make them all either reduction reactions or oxidation.
Exactly.
And then you find the most positive.
Exactly. If you make them all oxidation, the most positive one is the best oxidizer. But in this case, what Nabil did is he flipped these 2 because he knew he wanted the best reducer, so he just made them that way. Exactly. Okay. And then you could ask here, what is the best oxidizing species? Okay. What do you think the best oxidizing species is? Zinc. Okay, because the most negative one of all the reduction potentials is the best oxidizer. So zinc, specifically Zn. Not Zn2 plus, Zn. Oops. Okay. Side note, real life application, this is why zinc is used to coat nails and metal and stuff like that. It's called a sacrificial metal. So instead of the iron rusting, the zinc oxidizes first because it's better oxidized than iron, and it prevents the iron from rusting.
That was on our wall.
Yeah.
Wow.
Okay. So this is why you coat it with a metal that has a better oxidizing potential to protect the metal that you really actually care about. So if this is our best oxidizing and best reducing species, then what is the cell potential for the greatest? I'm not wording this right. I think, okay, I think you know what I mean here, but I didn't word it correctly. The question is, what is the cell potential for the greatest reaction? So which reaction would generate the most voltage? That's what I'm trying to say. Okay, so which 2 reactions would you be using?
This.
Those 2, exactly. So you would use Ag plus electron yields Ag, which is 0.80, and you'd use Zn yields Zn2 plus 2 electrons is 0.76. And it would be 1.56 volts. If you're trying to make a voltaic cell, your voltage should always be positive. Okay? Sorry, I'll give you a chance to write this down and I'll say it.
How do you have the spontaneous and not again?
If the cell potential is positive. And we'll talk about that when we solve for delta G in a little bit. Oh, sorry.
Huh. And then if you wanted an electrolytic cell, you'd want it negative.
Well, it would end up being negative because if it was positive, you just let it happen naturally, right?
Yeah.
Now, please be careful when you're doing cell potentials, okay? Books will often tell you to do reduction minus oxidation, but they don't flip the values. They just take the values of reduction potential and subtract. I like flipping and then adding, okay? Because flipping and adding makes it make sense. Don't do both. Sebastian was having an issue with that yesterday. He kept asking, he's like, okay, so it's reduction minus oxidation and you flip it. I mean, no, don't do both. Because if you think about it, if you do both, there's no way you get a negative number, right? So that can't be right. You do one or the other. I like to flip and then add. Now, what's my overall reaction when I combine these two half reactions? 2Ag plus Zn. Okay, what's my voltage for that?
1.56.
Why is it 1.56, Adriana?
Oh, why does it change?
Yes. Because this is a cell potential. It doesn't matter how much you have of it. It is a standard potential for that reaction. So if you double it because you need more electrons to cancel out, that doesn't affect your potential difference. So you never multiply your cell potential by any numbers. Never. The only thing you ever do is change the sign, that's it.
Wait, why?
Oh, because the cell potential is in kind of innate value to that reduction or oxidation reaction. It doesn't depend on how many moles of it does that.
But like enthalpy.
Yeah, enthalpy is measured per mole. A potential difference doesn't matter how much you have of it. It is kind of standard here. So, because if that were true, then your potential would change based on which metal it reacted with, and it doesn't. It's always that standard value. Okay. Questions about that? So in your voltaic cell for higher level, you might be given half reactions and be tasked with setting up your own voltaic cell. So you'd have to figure out what's your best reducing species, what's your best oxidizing species, and then calculating the cell potential. Questions on that? Okay. Next topic is aqueous solutions. Okay. Aqueous solutions and electrolytic cells. This still incorporates some cell potential, and that's why we're kind of transitioning into this. What you have to think about is that water can undergo both oxidation and reduction. So when you have an aqueous solution, you have competing reactions now.
So like the hydrogen gas bubbles, right?
You will have the water possibly oxidize and reduce, and then the ions of the salt possibly oxidize and reduce. So, water can form O2 gas plus electrons if it's oxidizing, which has a cell potential of negative 1.23. And then water can reduce which has a cell potential of negative 0.83. Luckily for you, these are given to you in your data packet. The bottom one, more direct, the top one in reverse because the chart is all reductions. So look for the one with water on the right by itself, and that's the oxidation of water. So now those two reactions get involved in every electrolytic cell. You have to determine whether they're happening or not. Okay? I would know these because I think sometimes on the multiple choice they like to ask about this. They like to ask what product will be produced at the anode and cathode of an aqueous solution. So don't just rely on the data packet to tell you this stuff. I would still know these reactions. Really, yeah, I would know these reactions. So for example, if you have NaCl aqueous, you have possibly the Cl minus becoming Cl2, which has a cell potential of negative 1.36. Or you have the water as negative 1.23. Okay. Now, which one, according to these values, is the better oxidizer? Water. Okay. So this one is the better oxidizer, but not by much. Okay. And that's where this is a little tricky, because the cell potential difference is so small here, like at 0.13, that if you add too much salt, you may actually get chlorine gas instead of water. Okay? It's because chlorine has a negative charge, and that attracts it to the anode better than the water. So if you have enough Cl minus, it can get through all the water and oxidize there. So what you have to remember is that in dilute solutions, you get O2 gas, and in concentrated solutions, you get Cl2 gas. This is the only time that really happens. It's a very kind of unique circumstance. Yeah. This is how saltwater pools work, right? Saltwater pools, you dump a bunch of salt into your purifier, and it uses the electrolysis to make chlorine gas, which then disinfects your water. Now, you have this, and you have this. Okay. Which one's a better reducer? Water. And it's not even close now. In fact, the rule of thumb is group 1 metals don't ever reduce in the presence of water. So you can always guarantee that if you have a group 1 ionic compound, that your cathode will always be H2 gas. Guaranteed. Never a doubt. Bet $1 million.
That's a lot of money.
Yeah. I carry that around just on a just in case of a rainy day.
Cash.
Yeah, $1 million. Never know when my car breaks down, I have to buy a Rolls Royce.
Okay.
This is just for the stream, guys. Okay.
What about a golf cart? Would that be more to drive on golf cart?
On I-10?
Yeah. I mean, there's nothing like the thrill of no doors.
And a speed limit of 20 miles an hour.
Why did people buy the cars without the doors and the windows?
Because they like to safari.
Like, you mean the Jeeps?
The interesting, you're saying that to an African, right? And I can't even notice.
Okay. It's just kind of a sporting thing. It's just kind of a open air kind of experience.
There's
for them.
cars with no doors.
Yeah, like Jeeps, you can take off all the doors and like all like the windows and stuff like that. Yeah. Okay. So,
Safaris other places.
all right. You combine these reactions as well. Okay. So, for example, in dilute, you would combine this reaction and this reaction. So then you end up getting, essentially, H2O yields 1/2 O2 plus H2.
If this is gonna sound really dumb.
Yeah.
H2O is like reacting with itself. Like.
This is the best oxidant.
Yeah, it's the best oxidizer and the best reducer. So water will both oxidize and reduce, yes.
Is this
So that's what's happening.
Yes.
Is this a?
But it doesn't react with itself. It reacts with the anode and the cathode.
Could it sound something?
Yeah.
But what even is like the anode? It's just like a metal.
Platinum, something that's
Okay.
unreactive, like graphite or platinum. Yes, Nabil.
Wait, so the top set of equations is at the anode?
Yes, the blue ones are in the anode.
Okay.
The green ones are in the cathode.
Okay.
Yeah. Okay. Where it gets tricky for aqueous solutions is with copper sulfate, and that's one that they like to ask about. Because copper sulfate depends on the electrodes that you're using. So the thing with inert electrodes, that implies that there's no copper metal to oxidize. So that makes up your decision about what's happening at your anode. Because at your anode, you only have one possible reaction. The water oxidizing. Because there's no copper metal to oxidize, there's no competing reactions. Sulfate doesn't do anything. Sulfate, the polyatomics, we don't worry about reducing or oxidizing. At the cathode, you have, this reaction, which is negative 0.83, and you have copper reducing, which is what, positive 0.34. Oh, what? Yeah, negative 0.83, yeah. And so, copper wins. So in this case, copper reduces and oxygen is produced. So on the cathode, you'll see copper metal. And on the anode, you'll have oxygen gas bubbling. Yes, Adriana?
Okay, you explained this, but it didn't get into my brain.
Sure.
But why in the anode is it like automatically H2O?
Because A, sulfate does not oxidize. And B, there's no copper metal in its neutral form to oxidize. So that's the only thing that could possibly oxidize water.
Oh, because it's in the compound thingy, so it'll be Cu2 plus.
Yes.
Okay.
Yes, so the only form of copper you have is Cu2 plus in the solution. Now, this one is also interesting because you want to know the observations. Okay? So knowing that these are the two reactions that happen, okay, what are some visual cues that you can take from this reaction? Yes, Nabil?
Bubbles at the end.
Bubbles at the anode is one. Okay? Okay, right. So let me list those. Okay, so bubbles. Oops. On anode. Copper metal. On cathode. What else might you observe? No. What else do you notice the anode producing?
Oh,
H plus. So what else is it going to change?
It's gonna, the acid.
Acidity. The pH will decrease. With the pH probe. Well, what you do is you put phenolphthalein in your solution, and then it'll change colors
Why is it gonna decrease?
because of production of H plus.
if I actually like
Isn't it? Oh yeah. It's getting more sense. I'm so sorry. My brain knew, but.
It's okay. Seth.
if I actually said like a lack of bubbles on the
No,
cathode,
it
because
wouldn't
like the H2 isn't being produced. It's like, oh, you can tell it's like.
For those of you watching the stream, I'm shaking my head vigorously no to tell Steph she can't say that.
It is quite vigorous.
Thank you.
You're not shaking your head at all.
I'm not now.
You were
Okay. One more visual cue. Okay. Where is that copper metal coming from?
Oh, yeah, anode is being
The
broken
solution.
down.
The solution.
The solution.
So
The
Megan,
solution changes color.
so what's Megan? Do you know what solution? What happens?
It becomes less blue.
Thank you, Megan.
Oh, sorry.
Wait for why?
Because the solution's blue because of the copper ions in it. But when the copper ions are reducing and being pulled out of solution, it becomes less blue. So solution becomes
My whole idea was transition.
less blue. Toward colorless, if you want to say that.
It's what are the transitions like copper's blue.
Iron can be like kind of reddish or brown. Cobalt's a very kind of, well, actually it has two colors. It has a red and a blue complex ion, so it depends. Depends on the ligand. So you'll be able to say these observations if they ask you for that. Now, if you do copper sulfate in copper electrodes, now you have to change things up because now you have copper also oxidizing as well. Possibly. But spoiler alert, it is true.
I
Okay.
haven't seen the movie yet.
You're behind.
Watching it live.
Okay.
We did have a lesson on this earlier in the year.
Yeah. Here. So notice that copper's oxidation potential is greater than water's. So it does end up oxidizing. And it ends up reducing. So here, you're just converting copper metal in the anode to copper ions and then putting that copper ion onto the cathode. Okay? So do you have a net reaction here? No, there's no actual net change. Everything cancels out. Right. So, are you going to see a change in pH? No. Are you going to see any bubbles? No. Are you going to see any color change? No, because the amount of copper that's being put out is being put back in. So no visible changes are going to be occurring if this is happening. Okay? Then what's, yes, Nabil?
What, so there isn't any like copper deposition?
Oh, sorry. Yeah, that's the one visible change. Sorry. There is copper metal still being plated on the cathode. Sorry, you're right. Copper metal being plated on the cathode is still occurring. What is the purpose of this type of reaction then? Why would we do something like this? Why would we have copper electrodes then? Yeah, Nabil?
Electroplating?
It is kind of electroplating, and it's also the fact that you can purify copper from impure copper sources. Like, remember? So what you have is a diagram like this. Where you have like impure copper on the anode, and then only the copper oxidizes, and then you collect the copper on this side, on the right side. So, like Neil said, you do want to electroplate, you want to purify it and electroplate it on the cathode, but you, for your anode, you want impure copper, because you only want the copper to come out, and then you can collect it over on the cathode. You're always collecting the metal on the cathode. That's a good rule of thumb.
Kind of cool.
Yeah, kind of. Questions about that? Yes.
I'm so confused with the positive and negative.
Okay.
How do you know?
Yeah. So here's, so you're saying, how do I know the positive and negatives for the electrodes?
Yeah.
Okay. I think the way I want to think about it is, in a voltaic cell, the reaction is spontaneous. So the electrons are being already naturally pulled toward the cathode. So relatively, the cathode is attracting electrons, so therefore it must be positive. Because that's the only type of charge that can attract electrons in that direction. Okay? So in a voltaic cell, the cathode is positive because it's pulling the electrons toward the cathode. Okay? In an electrolytic cell, you're trying to force the cathode to cause reduction by drawing ions toward it. Well, those ions need to be positively charged. So therefore, the charge of the cathode needs to be what? To attract those positive charged ions. Negative, exactly. That's the kind of concept. So the electrodes kind of serve a different purpose in both the cells.
Okay.
Does that make sense?
Like I've always just known that they were switched, but I've never like tried to
Yeah.
read.
So the voltaic, it's negative, it's positive because the electrons are flowing in that direction naturally. In electrolytic, you're trying to force something to happen that doesn't naturally happen, so you flip the charges to force something to reduce that normally wouldn't want to reduce.
Is that whole like chemical to electrical?
Yes,
energy?
yeah.
Okay.
Yeah, in here you're putting electrical energy in to create chemical potential energy. Yeah. Yes.
So that battery thing, you know how you have like a shorter line than a
Yes.
longer line? Do those mean anything, their orientation? Or
Generally, the longer line is positively charged. That's the notation for it.
And
so
so they'll probably tell us.
I believe so.
Yeah.
Wait, but like, an electrolyte, it like doesn't matter that the cathode is negative in terms of the electrons thing,
No.
because you're like,
Yeah, the battery's providing the electrical flow itself.
okay,
What the purpose of the cell is to force something to reduce that normally wouldn't force. And so you don't worry about the electron flow because the battery is overcoming any resistance that you have by putting more electricity through it. Then that would want to go backwards. It's kind of overcoming that resistance. Does that make sense? Okay. Electroplating. Okay. This is when you place a solution into an electrolytic cell and you run a current for a certain amount of time to see how much metal you get. Okay? And there are three factors that you have to take into account here. The current, which is in amps, which is, coulombs per second. And then there's time, which is in seconds. And then the charge of the metal. Okay. So the three factors that affect how much you can electroplate are A, the current you use, B, how long you use it for, and C, what type of metal you are trying to electroplate. Because a metal with a greater charge requires more electrons per mole of metal to electroplate. So the equation that you need to know. Charge equals current times time. So the charge is equal to current times time. Also, charge is equal to Faraday's constant times the moles of electrons. So F is Faraday's constant. Okay. And C is charge. Okay. Which is 96,500 coulombs per mole of electron. Then you have to know, once you figure out the moles of electrons, you have to figure out what the ratio of moles of electrons is to the moles of the metal.
Is that why that like condensed equation you showed me?
Yes, we're going to get to that. I'm going to show you kind of how we get there. Because I feel like to save y'all time, it's probably just the easiest way to do it. Okay. So, essentially, the moles of metal that you can make is equal to the moles of electrons divided by the electrons needed per mole. So let's say you have Al3 plus 3 electrons to form Al. The moles of the metal would be equal to your moles of electrons divided by 3, where N equals 3. Where N is equal to the number of electrons you need to make 1 mole of metal. For Na, sodium, it would be N would equal 1. For Mg, N would equal 2. Like how many moles of metal you can make. So like, let's say aluminum, you had 3 moles of electrons, right, Adriana? Every mole of aluminum needs 3 electrons, so 3 moles of electrons would make 1 mole of aluminum. Does that make sense? Because that's the moleable ratio, 1 to 3, right? Okay. Now I'm going to show you a little bit of a trick, and this is kind of algebra substitution. Okay? We'll say this is N, because N is the number of electrons you need. So guess what? I can say my moles of metal is equal to moles of electrons over N. Okay. What is my moles of electrons also equal to equation-wise? C over F. So I'm going to do some substitution. This means C over F times N is equal to my moles of metal. Okay? What's C equal to? IT. So the moles of metal is equal to I times T over N times F. Little shortcut. So if you want to find the moles of metal, you do the current times time in seconds divided by the number of moles of electrons you need divided by Faraday's constant, which is 96,500.
And that tells you what, like how much you
You would make, how much you would plate. And then if you want to go to grams, you could just multiply by molar mass. But I think this is a fairly easy equation to kind of figure out. If you don't like it, you just like to do stoichiometry, that's fine, you can do that too. Yeah.
So, how are we most likely going to be like knowing our moles of electrons?
By the knowing the charge of the metal.
Okay, so like they'll give
Yeah,
us something.
yeah, they'll tell you what metal solution you'll be dealing with. So they say silver, then it's Ag plus 1, so 1 electron. They tell you calcium is 2 electrons. Aluminum is 3 electrons. So you'll know from the problem how many electrons you have to deal with. So that's the magical equation right here. Moles of metal equals IT over NF. But again, if you don't like that, you can do it step by step. You can take the charge times time equals, a charge equals current times time. And take that charge and divide it by 96,500 to get the moles of electrons. And then take the moles of electrons and divide by the number of electrons you need to get the moles of metal. It does the same thing. Questions about that? Excuse me. Thank you. All right. Let me check something real quickly because I think this might be the last major thing that we're going to talk about, but let me just double check just to make sure. Don't want to get your hopes up and then.
I keep my standards low.
Yeah, I think this is the last major thing we'll talk about. Okay. Cell potential can relate to Gibbs free energy. And that is delta G is equal to negative NFE naught. Okay. So if you're given the cell potential, you can figure out the Gibbs free energy of that electrochemical reaction. Now, be careful because delta G is equal to N is moles of electrons, F is Faraday's constant, 96,500 coulombs per mole of electrons. And then electrons, cell potential is joules per volt. Sorry, joules per coulomb, which is volt. So when all the units cancel out, you're left with joules. So keep in mind that when you solve for this, delta G is in joules. Units are really important. Okay. So the idea is this: if you take, the moles of electrons, and let's go back to the one we did up here with the zinc and silver. This reaction right here. Okay, the number of electrons being transferred is 2. Because that's how many were canceled out. So 2 times 96,500 coulombs per moles of electrons times the potential, which is 1.56.
It's mental math.
Oh, is it now? I guess you're more mental than I am.
It's like 230.
Negative 301,080 joules. He tried to do like 9 times 1.5 times 2, and then it was really disappointing.
No, it was more of a 18 plus 4.5.
Wait, can you repeat again how you determine the moles of electrons?
Yes, the moles of electrons are the number of electrons that are canceled when you combine two half reactions. So that number of electrons that you have to cross out, that's your
In
N.
order for that species to
Yes.
do the thing.
Correct. So up here, for this one, we had to multiply this one by 2. So the electrons would cancel out. So the net electrons cancel by 2.
Okie dokie.
Up here, it would be because 12 is what we cancel out. So just keep that in mind. Okay, but yeah, that's a way that the IB could relate Gibbs free energy topic 16 to topic 19 by having you calculate the cell potential in part A, part B calculate the delta G, and part C determine whether it's spontaneous or not. Okay, so spontaneity means what kind of delta G?
Negative.
Negative.
Or 0.
So yeah, negative G or 0. So that relates to a positive cell potential because what? N and F are both positive numbers, and you have a negative NFE. So E is the only value that can affect the sign of delta G. So you want a positive E, so that it's spontaneous.
I agree.
Good.